Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series, but this is more of the applied math side. So I haven't been doing videos on applied linear algebra as I've been doing more videos on the conceptual part. So, well, for me, I actually have a midterm in like 2 days. So what I'm gonna do for this video is I'm gonna talk about basically everything that my professor discussed so far for this class. So this class is actually applied linear algebra and numerical analysis. Okay. Now, I guess just to give a brief intro of what this is, well, we want to basically have a foundational understanding of linear algebra, which we've been doing. And we also want to determine its applications and role in computer algorithms, which form, well, the core ideas of numerical analysis. Okay. So, right, for this midterm review, I'm going to be going over lectures 1 to 10, and I'm also going to be going over homeworks 0 to 3. Okay. Right, so let's just hop right into it. Let's get started. Let's go with lecture 1. Now, what we discussed in lecture 1, well, besides the syllabus and all of that stuff, and the motivation, well, actually, you know what? Let's discuss the motivation behind this. So let's actually motivate. Okay, maybe I'll just do like intro. So the motivation behind linear algebra and numerical analysis. Well, okay, let's actually first define what is linear algebra. So we say that this is a mathematics field or mathematical field. So there are different branches or different fields of mathematics. There's algebra, there's geometry, there's calculus, there's linear algebra, there's topology, and all different sorts of stuff of making meaning with the world, right? And linear algebra is a mathematical field that studies so we do finite dimensional linear objects. So we're not going to talk about non-linear stuff. Here we're focusing more on linear objects. And some of you may have already heard about vectors and matrices. So this is how we're going to compute them numerically. This is how we define them. And we did talk about this conceptually, what it means to have vectors and matrices geometrically, from a geometric perspective. So here is actually a fundamental set of tools. So we're going to be using just a bit of calculus here. So calculus is again the study of how things change, right? And there are many mathematical ways to define change. I'm not going to go in deep into that. You can check that out in my calculus series on which more advanced ideas are built. So we're actually based off of calculus, we're going to look at more advanced ideas. And I think we've been doing that already in my linear algebra series. So you guys can feel free to check that out. So that's linear algebra, that's calculus. In this course, we're talking about applied linear algebra and numerical analysis, which it's not so different. but the course is more focused on adaptation of these ideas. So we adapt ideas from, I'll call it LA, linear algebra, to basically algorithms and different kinds of methods implemented on a computer. Okay. So I hope some of these techniques might help, or some of these tools might help when someone's solving a problem using a computer in the future. Right. So they basically turn your computer into a supercalculator, or in this case, we call it a supercomputer, and they can solve massive problems. And there are some examples here, but I'm not going to go through them anymore. But there is one latest idea that's been going around. It's a buzzword called AI, artificial intelligence, neural networks, LLMs, machine learning. So linear algebra, linear algebra is actually a building block of AI and machine learning, right? So these are foundations for understanding what AI and ML are, ML machine learning. Okay, so that's the idea of the motivation behind it. Maybe I shouldn't do an underline. Now let's actually talk about the topic itself. So we're gonna start off with talking about vectors in D dimensions. So these are the primary objects, right? The primary objects, or I guess we could call them data structures, doesn't matter too much. So that's what vectors are. So these are going to be the primary objects in this course, and we're going to make them finite dimensional vectors. So everything that we're going to talk about is the core of everything is based off of vectors. And so we're going to be building off of that. Now let's do an example here. Let's try to do a brain tease. So in 2D or 3D, a vector can represent the following. So there are lots and lots of ways to represent this finite dimensional object. So we could represent it as, so geometrically, the location of a point, or we call this sometimes an object. So this one we've learned in algebra, or no, geometry, I forgot. Cool, man. So say we have the typical XY axis, and there's this point here. We can draw it. We can draw a vector out of it from the origin, and we can call this the V vector. And this point, let's say this is x is 2, this is y is 1. It's not drawn to scale. So this is the point 1, 2, right? So this is from pre-calculus, from algebra. We're going to draw a vector out of it. So what do we call this? We call this an object, right? This is the object in 2D space. Now we have different kinds of notation for it. For this course, I'm going to use okay, let me just write it out. Now, if you've seen me from my past videos, I have been using this notation a lot, mainly because it's a physics calculus. I've taken calculus-based physics, And so when they introduced vectors, they used this notation. When I was taking this class, this was the first notation. This was the notation I was introduced, these two, right? And so for this class, I'm going to use this. Hope it's not too confusing because it's the same thing. Right. Okay. So say we have, so that's our vector. So going back to the example, 2, 1 is our vector where 2 is the x coordinate and y is the y coordinate. Okay, easy enough. Now let's go to 3D. So say we have this vector and it has these components, right? So this would be the x coordinate. This would be the y coordinate. This would be the z coordinate. So this is from 3D calculus, right? So say we have 3D space here. Z, X, Y. So the way to gain access to this point is from the X coordinate, we move 2. And then, so let's say 2 is here. From the Y coordinate, we move 3. So let's say 3 is there. We come across this. And then from Z, we move 3 again. So maybe here is 3. So that should be around here. And we can make a vector out of that. And we can call it vector V once more. So that vector V is pointing to this object. Okay. So that's one way of representing a vector. We can think of it as a location of a point in space, whether that's in 2D space, in 3D space, and to be more general, in some d-dimensional space or n-dimensional space, whatever you want to do. So what if we can also represent a vector in other ways than just a location in space? Maybe we could represent it as, so if we've taken physics, we know what a velocity is, right? I haven't taken physics, so I don't know. But something like this. So for instance, maybe a way to represent velocity is, say we have this vector here. And okay, here we're going to make it general. V sub x. Sub x means x coordinate. We're not going to put a number in there. We're just going to say they are arbitrary numbers. Uh-oh, what's happening? I opened an app now. I'm lagging. V sub y, V sub z. Okay. And I guess the way we can define this, we can again do a 3D space, right? And say we have this planet and it's orbiting around like so. And at a particular point, that's where the V vector is. So that's how we can represent this idea. So if we've taken calculus 3, there's a name for this. Or there's this idea of what we call, actually I forgot, something about motion using vectors. We can represent it as something moving. Okay. I'll write the physics notation. And I think we've seen this before, because especially for those of you who've been watching my videos in the calculus series, maybe you've seen something like this. So this V vector represents V sub xi plus V sub y j plus v sub z k, the ijk format, right? So probably most of you have seen that when you've taken calculus, or at least when you've watched my video in calculus. So in this course, we're generally going to work with vectors in d dimensions. So in this course, we're going to think of it more. So the way we're going to represent it, we're going to think of it more as a list or collection of numbers. Or another way to call it, scalars. If we've seen If you've seen my previous videos on both linear algebra and calculus, sometimes we call these scalars because it's used for scaling. So the way we would represent this idea is, for instance, say we have this vector and then we have this notation. So this is not too much of a notation, but this just means it's an element of, or it belongs to the real number set, D, meaning it's in D dimensions. And we say that this vector has components v1, v2. So this is a more general idea all the way to D. And we cannot visualize D dimensions, right? I think for me, it's impossible. As of now, I don't know if there's a way, but I can't think of visualizing a 4D or 5D or 100D, 100 dimensions. And we say that, so here I'm just throwing in notation, but what I'm essentially saying is generally, we think of a vector having some number of dimensions D in general, not just 2D, not just 3D, but D dimensions. And so accordingly, we have D components. We have D numbers inside the vector. Because here in 2D, we only have two numbers, X and Y, 2, 1. In 3D, we have three numbers or components. I'm going to call it components now. So we have three components, so we have 3D. But in general, D components, so we have D dimensions. And that's actually a fact that we're going to look later on. Okay? And we also say that all of these components inside the vector are real numbers. They belong in the real number set. Okay? So here we say they are what we like to call scalars, or another way to call them is real numbers, meaning they're not complex numbers. That's essentially what I'm trying to point out. So to give an example, well, let's say we have this vector V, which has three components. And so this vector, since it has three components, it's not in D, it's in 3. Well, D is 3. D is equal to 3. Another example, let's try maybe 1 to 1.3. Let's throw in a pi, why not? 0.1. So how many components are these? Oh shoot, I messed up the notation here. 5 components. So that means this is in 5 dimensions. Okay. Right. So when working with vectors in D dimensions, let's define two basic operations on them, right? So we're going to define two operations on them motivated by how vectors are used in 2D and 3D. So we're going to look at, okay, this one I'm kind of deviating from the lecture to look like, we're going to look at basic operations for vectors. So these are some things we can use to work with vectors. And let's generalize it to d dimensions. So for instance, we can do from elementary school or from kinder or from childhood addition. We all know what addition is, right? So given v and w vector, and let's say they're both d dimensions. So they both have the same number of components. So we say, okay, another way to represent them, we can say they're going to look like this. And w is probably going to look something like this. I hope this makes sense. I'm just throwing stuff around that I'm trying to make sense of. So based on these two vectors, we can define that v and w, when we add them together, we're actually just adding their components, their corresponding components. So let's say v1 is w1, v2 plus w2, and we keep going to, so we're adding all components here, vd, wd. And we're going to say that this sum, v plus w, is actually just also in RD. How do we know? We just added a bunch of numbers together. We didn't really change the size of the vector. There's no new number here. Nothing. It's just d. So, side note, v plus w is also a d-dimensional vector. It didn't change. Cool. I hope that makes sense. Now, next part we're going to talk about, or at least the next basic thing we can do, is multiplication. Now, why did I call it scalar multiplication? Because we're multiplying a vector by some scalar. Now, what did I say about scalar? It's a number. So let's say given, say, vector v, and it's in d dimensions, and let's say we have scalar alpha, and this is just a real number, right? It belongs to the real number set. So alpha is just a real number. It's just a number. We're not saying it's an angle or anything. It's a real number. So we're going to write, so alpha times v is just alpha we're just multiplying alpha to each component of the vector. And this belongs in RD still, right? Because we just multiplied it. So we also say that alpha multiplied by a vector is also a d-dimensional vector. So we're still getting a vector out of it when we scalar multiply a scalar, scalar multiply a scalar by a vector. Now let's do some examples so that we don't get bogged down by theory. Say, okay, let's say alpha is 0.1. And let's say this vector v is, it's 1, 2, 1.2, 3.1. And let's say w, okay, we're doing another vector here, is 0, 0, 1, 0. So let's try to practice some scalar multiplication and addition. How about, let's do this, alpha times vector v plus w. So actually, the funny thing is, this also follows PEMDAS, right? So we say, okay, we have a vector. So we first start with multiplying 0.1 to v. So that's going to be 0.1 times 1, 0.1 times 2, 0.1 times 1.2, 0.1 times 3.1. And then that's a vector in it of itself. Then we're adding it to W of, oops. So W is 0, 0, 1, 0. So again, when we add them, we're going to get this resulting vector of, actually I could do it here, 0.1, I think this was 0.2, and this was 1.12, and this was 0.31. I hope that that's correct. Right? So it's just basic addition and multiplication that we're doing here. Now you might be, okay, so far I hope everything makes sense. Okay. If not, you can roast me. Right. So these two basic operations, now you might be wondering, where in the world is division and subtraction? Where it's coming, don't worry, are enough for us to build vector subtraction. So from vector addition and scalar multiplication, we can now do vector subtraction. How? Let me show you. We do, so let's say we're subtracting two vectors, right? This is actually the same thing as, say we have vector v. We're adding it to a scalar multiple of -1 times w. So here we combined scalar multiplication and vector addition to get vector subtraction. So this is just the same thing as v minus. So we're going to do it to all of the components. So v minus w, 1, 1. We're doing it all the way to v, what was this? I'm assuming d, right? So that's how we build off of what we've learned, and now we have vector subtraction. So let's do an example of it. So say we have, let's try this. So based on what we have here for alpha, v, and w, so here we have v minus alpha w. This is equal to v plus -1 alpha w. And this is the same thing as this guy. So now we're just writing off of them. We're writing vectors themselves. 3.1 plus 0, 0, 0.1, 0 equals 1, 2, 1.1, 3.1. Okay, and that's it. So far, so good. I hope so. And that's it for this video. That was lecture 1. It was really just a brief introduction of what's about to come. So now we've checked off of lecture 1. And so the next lecture, of course, I'm not going to do it here. I'll do it in the next video. But just to tease it a bit, next lecture, wait, what was the next lecture? Right, next lecture, let me see. Even I forgot what we were talking about. That's why I was doing a brief review. We're going to talk about, so you might have already seen this. If not, that's good. I'll explain it from bottom to up. This was a very confusing topic for me. but I'll explain it in a way that you can understand. We're going to talk about spans and linear independence. Okay, so that's it for this video. I hope you guys enjoyed, and I'll see you all in the next one.